Hello and welcome to the quick tutorial and demonstration on the VPforce DIY kit that includes two motors and the main controller. Okay, I have the motors power connected to the power strip. Power is hooked up to the power supply. USB cable is connected and the board is currently powered on. We can see the interface and data is updating now. It's trying to communicate with the motors, but the motors are powered off at the moment. Also, I can demonstrate the anti-cogging feature. Uh, the, the motors are powered down, and as you can see, the movement is not smooth. This is due to motors' inherent cogging. Okay, now I will power on the motors. We have an audible indication that the motors have powered on, and motors now are buttery smooth. And we can see on the interface it now indicates the position of the motor for both axes. Okay, the first thing to do when powering on the board is to calibrate the motor range. So there's the auto calibrate feature, and if you press that, it will reset the minimum maximum positions, and then you can move full movement of the joystick you're building. Let's say, for example, in our case, from one side to the next for both motors. And as you can see, the numbers that match those positions are updated in the sensor calibration fields. Okay, calibration is now done. You can turn off the auto calibrate and we can send the configuration. Motors, when receive the new configuration, they excuse me, not motors, the main board beeps when it receives a new configuration. And it double beeps when the configuration is stored to the flash memory. So we press store config, it beeps in quick succession 2 times. Okay, motors are now. Also, for example, if your joystick device has a reduction, a gearbox or of some sorts, it's also possible to calibrate multiple rotations. I'll do just now. I'll press auto calibrate, and I'll okay, like that. For example, you can see the position moves more than one rotation, from 7,000 to minus 7,000, for example. Okay, I'll send the configuration. Okay. Oh, forgot to calibrate the next. Okay, done, and send config. Okay, this one moves from that side to that side. Ooh. And this one, you can see it. You need to turn it multiple times. One caveat of this solution is that if you start up the motor when it's not in the central position, it will start up in a wrong position. In other words, you need to start the motors up within 1 revolution of its central position. Okay, I will recalibrate them now. Oh, sorry. Okay. Done and send. Okay, it's good now. Okay, let's go through the main options. So the max motor current, this value is set the maximum commanded current the motors will receive. If it's set at 20 amps, no more than 20 amps will be requested from the motors. Next one is maximum power supply current. So this is to limit the maximum power drawn from the power supply. I've set this at 4.3 amps since my power supply is a bench power supply which delivers maximum 5 amps. Next one is neutral damping compensation. This works like power steering system in the car. Motor has some inherent damping. For example, if I set it at 0 and send the configuration, I can feel a slight resistance when turning the motor. And if I increase the neutral damping compensation a few percent, it moves more easily. But if I overcompensate, it will move by itself basically. Let's see, if I nudge it, and it goes. It amplifies too much the movement. So we need to be careful with the setting and not set it too much. 4 to 5% works the best for these motors. Some configuration, great. Now, spring strength proportional damping. This one is used to increase the damping ratio when spring force is increased. This is basically to prevent oscillation when spring coefficient is too much. Let's say I could demonstrate this. I'll set it at 0 for now, and I'll go to the effects page, turn on the spring. Okay, the spring is at maximum strength, and now I'll start with this one. Let's say at 20%. Okay, I'll save, and the motors are centered now. 5. Okay, yeah, you can see it oscillates. Now, if I increase the spring strength proportional damping, still, let's see, at 20%, much less. So this works according to the specified spring strength. For example, if I increase to 40%, no, it damps even better. Increase more. Yeah, but without this, it could wildly start oscillating. Dangerous a bit, but I'll try to reduce it. Okay. It's still stable. At 30%. Yeah, it damps those oscillations. Yeah, I can now reduce it. So, next section is input filtering. These values are for low-pass filters, which filter the incoming values from the motors. So this one is for position, which are these values here, and the velocity input filter is for the values here. Generally, from my testing, the better is to leave them off. 0 means the filter is disabled. You can test it, try it out. Generally, very experimental values, these ones. The acceleration PI gain, it's for controlling the acceleration estimator. Basically, it's a mathematical tracker which tries to track the velocity, and from tracking the velocity it gives us the acceleration. The higher this value, the tighter it tries to track the velocity signal. Generally, the higher this is, the more unstable the control loop becomes. So if turning on the inertia effect, and if you notice the instability, you can reduce this, you can reduce the inertia maximum strength, or reduce the output filters. So for damper and inertia, this one is here. For my testing, 2 Hertz is the most stable, but increasing it to higher values makes the system's bandwidth higher, and thus it can become more unstable. So we can try the inertia effect right now. Okay, it's 37%. This one is at maximum. Okay, and let's send the configuration. Now if I try to move, it feels like mass is attached to the motor. Feels like, yeah. No, it's came off. Yeah, this one is better. So let's try increasing the inertia. Yeah, it feels much more resisting my movements. So I can demonstrate how the inertia works. For example, if I nudge it, it keeps moving. It resists change in velocity. So it's a very cool effect to simulate high inertia of the, for example, control column in the aircraft. Now let's try to make it unstable. I'll increase it more. Usually high frequency external interaction causes the oscillations, but it's quite stable at the moment. But if I increase the damper inertia frequency, low pass filter, that might cause it become less stable. Yeah. It started oscillating. So be careful with this. Yeah, 2 Hertz, it works quite well. Also, when using inertia with dampers, it's also makes the system less stable. So let's turn on the damper. Now the damper is turned on with the inertia, and okay, I'm holding tightly, and I'd better reduce a bit the inertia. Okay, let's see. Okay, it's stable. Let's increase it more. Still stable. Let's increase it more. Still stable. So yeah, 2 Hertz works quite well. if I increase this, I have high confidence it will start oscillating, so I'll leave it there. Spring and other effects, output filter is similar. For example, if I turn on the spring, okay, I'll start with lower spring gain. Okay, let's try it now. It tries to recenter, but because we have damper turned on, it resists change in velocity. Okay, let's try increasing the spring gain. Okay, now the spring is tighter. It goes back to center faster now. Okay, increase more. Yeah, it goes even faster. But there's slight oscillation I can see when I release it. This is due to the quick change in the dynamics. So yeah, those all those effects, they have interactions between them, and increasing gains too much while all the effects are enabled increases the chances of the system becoming unstable. Okay, now I'll turn off these ones and turn on the friction. Friction is similar to the damper, but the main difference is the friction effect is not dependent on speed. It basically resists a fixed amount of force when the motor moves. Okay, let's try the current setting. So yeah, when it moves, it gives a constant opposition to my movement. You can see in the graph. Okay, I'll increase it here more. Yeah, now it resists more. Well, friction also can give some oscillation. So this one also filters the friction output. Well, in the future, I might introduce some more improvements in the control loop. But for now, it works quite well. Okay, one thing to note is that you can control the gains in real time using the potentiometers. There are two potentiometer ports on the board, which you can connect a generic potentiometer. And you can change, for example, the master gain or the spring gain during the game. It can also work as a direct input slider, which shows up in the joystick, well, basically as a slider of the direct input control. Okay, for example, spring gain. If I set the spring gain for the potentiometer number 1, it will adjust the spring tension between 0 basically and the value set here. So it will adjust the range from 0 to the preset maximum. So these sliders should be the maximum values that the system is stable. There's also the master gain, which basically scales all those values by the value set here. There's also the periodic effects slider. This adjusts the periodic effects which games might send to the joystick. For example, sine waves, square waves, vibrations, and so on. There are multiple supported effects by the USB standard force feedback. Okay, let's turn off the friction, and there's also the constant force effect. This basically sets constant exerted force, but it's not currently implemented on the firmware. It will be in the next revisions. So that's basically it for the settings. Well, yeah, there's also the grip. Generic grip means it just reads the raw information from the shift registers, and it passes them through the direct input system. Windows sees basically as is. There's a column here which represents the physical buttons from the grip, which is red. And I have a profile for the Whirlpool T50 CM2 grip. It implements the hats from the joystick, and also the analog brake axis also is implemented. Game sees it as an analog axis. There's also the debug tab, and it shows the info received from the controller. Well, it's basically to see what's going on, what effects are being sent from the game, etc. And also the loaded effects fields here. Here you can see the game and the preloaded effects from here. When you start a game which supports the force feedback, the loaded effects will appear here, and the values will be visible. For example, the spring center point, the coefficients, and so on. So it's good for debugging the various games. Also, I can comment on the values shown here. So XY is the position, which is read by the encoders in the motor. Dx dy is the velocity that's calculated from the position. D2x and D2y is the accelerations. Accelerations are calculated from the velocities. Now Fx out and Fy out is the forces that are outputted to the motor. These units are in 4096. Basically 4096 equals 1 or 100%. So those numbers are can be used as a reference. Raw X and raw Y is the raw position that is read by motor encoders. Forgot to mention that X and Y here is the calculated values used by the calibration. Potentiometer 1 and potentiometer 2, the current read positions from the potentiometers. As I said before, the current board is doesn't have potentiometers connected, so they show random values basically now. Current X and current Y. The current current of the motor in amps, it's showing non-zero values because the anti-cogging system is working, and it's doing its job by removing the cogging forces. Now, next, motor temperatures. Well, if I, for example, load the motor, let's enable the spring effect. Now, if I load the motor, you can see the amperage increases for the motor into 15 amps, and the temperature should rise shortly. There we go. If I recall correctly, from 60 degrees to 80 degrees, the motors start generating current, and because of the power dissipation, the current starts to drop when the temperature increases. Next, the I bus. This is the current from the power supply bus. If I load the motor, the current from the power supply increases to Next one is B bus, which is the voltage from the power supply. So yeah, that's the basic telemetry. One more thing to note is that if a motor faults, for example, if I set the current higher than the power supply, I can overload the power supply and it will drop the voltage. The motors will enter a fault condition and increase the spring gain. There we go. Now motors enter the fault condition. This is due to under voltage because the power supply dropped the voltage due to overcurrent condition. And a long beep indicates the motors have encountered a fault and a red LED starts blinking. I will document the patterns and the codes for the fault, and also fault condition should appear in the status bar in the software. I haven't currently implemented that, but it should become available in the next versions. And that's it for this video. Thanks for watching. See ya.